Thank you very much, and I'd like to re-emphasize what Garit just said. I feel like all the talks today were a precursor to my talk. Steve started talking about how climate is our most important factor, and several of the talks thereafter mentioned temperature. Okay, so the talk today is a synthesis of many lines of research with a little background to start and incorporates the work of all these people. The title is Incorporating Temperature into Production. Okay, so here's California's current, is this the pointer? Currently where the pistachios are planted in California. You notice the bulk of them. It's down here, and why? It's climate. The most important decision you will ever make in establishing an orchard is where the orchard is planted. And this is because climate is the limiting factor in tree crop production, particularly the limits. The upper limit, as Julia mentioned, photosynthesis, ceases because of enzymatic reactions to actually function above 105, or is very limited above 105 degrees Fahrenheit. And of course, as the citrus industry in Florida will show you, it's every year or every 50-year freeze moves the area where the crop can be produced. So climate is your limiting factor in tree crop production. And what is climate? Climate is temperature. All plants have genetically determined heat unit accumulation requirements for growth and yield. Over here, we show basically the optimal temperatures for pistachio production with the range, I'm going to make sure I get the pointer, with the range defined. And outside these limits, if temperatures are higher or lower, they have deleterious effects, okay? And all plants have, as I just pointed out, optimal temperature ranges effective at specific growth stages: dormancy, bloom, and here I'll outline these: dormancy, bloom and fruit set, fruit production, and edging into dormancy again. Temperatures, most of the temperature ranges we know now, as somebody pointed out earlier, I believe it was Julia, was that within the temperature ranges we get normal growth, but if we get unexpected higher or lower temperatures, these are going to affect the growth and the reproductive development of the plant. And the last thing I'd like to point out is temperature is uncontrollable. We have very few methods of mitigating it. Okay? So now I'm going to go back here one. I'm going to start and go through what we do know about temperature effects on these four stages of plant growth: dormancy, bloom and nut set, nut growth and reproduction, and entering dormancy. Okay? So, key temperatures influencing during dormancy. Basically, what we have is the baselines for total temperature accumulation. We actually know very little about variations during this dormancy period. As Steve and Julia pointed out, basically it's 54 to 65 chill portions. We use chill portions now more than accumulated heat units below 7.5 degrees centigrade or 45 degrees Fahrenheit, but that range is 800 to 1100. There is one report in the literature of temperatures influencing nut quality at the end at harvest, and that's a report out of Australia that stated that late February chill, the last half of February, because they did use dates, correlated best with decreased blanks. In this same study, he also, because he did this, what they called a contour study through the season, he found that the highest correlation with splits was steady, even heat accumulation through the summer. Okay. Key temperature effects during spring. This is one where we're starting to learn some lessons the hard way. Basically, spring is bloom and fruit set. That's the post bloom is when we get our shell growth and our hull and shell enlargement and formation. So bloom, date, and heat accumulation affect yield and quality of the nut. Specifically, one example we had, I believe, was 2004. Late April bloom and high temperatures resulted in decreased yields through increasing blanks and in decreased nut quality through low shell split, poor hull integrity, and low harvestability. This was work generated by Barbara Blanco-Alate and Julia Marino over the last 5 years. So basically, we do not know a great deal about the temperatures post-bloom and how they post-bloom and how it affects fruit nut quality. We are starting to learn a little, and as I said, through the hard way. Okay. Now I'm going to talk about the effects of heat during the growing season, during summer, post-bloom through harvest. And I'm going to start with the original model that was for growth that was developed by David Goldhammer and Bob Beatty back in the 90s. Basically, what they did as a function of date here on the horizontal axis, and as a function of size for shell diameter here, and kernel weight as a function of dry weight here, through the season, they defined 3 stages of nut growth. Stage 1, what they call fruit growth, this is shell and hull enlargement. Stage 2, they found nothing particularly happening, so they called that, but the shell was thickening and hardening, so basically they called that shell hardening. And then the 3rd stage, they called embryo or kernel growth. Okay, this model has worked very well for us until recent decades, when pistachio plantings were extended to different microclimates and where we're starting to have change in weather. Okay? Just to give you an example of the effect of microclimate, a former graduate student of mine surveyed temperature accumulation in growing degree days, that's here on the vertical axis, as a function of the day of the year. These were 30 different sites where pistachio production was possible based on the total accumulated heat units and chill units. And what she found was that here's 2 separate locations, here at about 180 days per year, and here at about 210 days per year, a difference of 30 days. They had an equal temperature accumulation of about 1,500 degree days. So if all growth and development is a function of heat, there is definitely going to be a difference in growth and development and maturation of nuts in these 2 climates. Doing your production practices by calendar is not going to be functional. Okay? So back about 2015, I started work with a graduate student and then a postdoc, Louise, the same one who did the dust work, to try and characterize pistachio nut growth as a function of heat units. We did 4 years of work. We sampled 8 locations stretched over 300 miles, sampled 6 cultivars, only female. We did not do male. We had a 7-day sampling interval, and our goal was to demonstrate that growth and ripening are a function of heat units, not time, not date. Okay? Basically give you a real quick idea of the procedures here. We got the nuts into the lab, we sorted them, we photographed them, we did measurements of size, we punctured them to get shell firmness through the season. We then separated the kernel and the shell and weighed them fresh and dry weight. And this is a general characterization of the data we developed. I believe this is for the Kerman cultivar. And what we showed was basically, here on the horizontal axis, we have growing degree days, the thermal units since flowering, and over here we have on this axis is from 0 to 100% of the factor we were measuring. For example, if I say I had 90% here, that would be I had 90% of the shell, of the nut shell growth completed. And what we found was, here's the nut shell in volume. we found out that within 500 to 1,000 days, the nut shell and hull were completely formed. Just yesterday, a paper came out of Spain that duplicated this work and placed the final nutshell growth at 500 growing degree days. For nut firmness, this was the biggest finding of this study, was that nut firmness, your nut continues to thicken and harden throughout the entire season, all the way through harvest. And then for embryo growth or growth of the kernel, that started at about 750 to 800 hours. So basically, we defined the 3 stages that Goldhammer, because we used his model of 3 stages, we defined the 3 stages as a function of temperature. Okay? Just to give you an idea of the differences in growing degree a day accumulation for the 3 major cultivars at this time, this is what we found out. For stage 1, Kerman and Lost Hills completed their shell development about the same time, whereas Golden Hills was about 50 growing degree days less. Stage 2, as I said, we found out shell hardening continues all the way through the season. There is no separate, discrete stage of shell hardening. It's merely a transition between when the shell has fully formed and sized and when the embryo or the kernel starts to grow. Stage 3, kernel growth, basically for Kerman, it started at about 1,000 growing degree days and ended about 2,000, 2,100. Lost Hills was almost the same as Kerman, slightly younger, but Golden Hills started at a good 200 degree days less and ripened almost 200 degree days less than Kerman. So these were the accumulations that were amongst the different cultivars. Okay. So we made just to show you very quickly, we made an online website for you to predict when your harvest timing might occur or when these different stages occurred. Here is the website, it's online and my signature. And we intended this as not a calculator, not like irrigation, but as a decision support tool. When you reach 75 or 90% of the parameter you're interested in, go out to the orchard and check it out and see if that is ground truth. So basically, if you go to this website, you provide your location by longitude and latitude, your cultivar, your bloom date. This website will look up the weather data, compute the growing degree days, and estimate the nut development dates as on a function of 0 to 100%. Okay? So there you are finding your location. There you are entering your cultivar, the date range that you are interested in, the percent that you want, a maximum that you want to flag. You can select from a number of weather databases to use and the historical date range you want to compare it to. The different weather models are explained on the website. And then this is what it'll give you. Down here, they've converted the growing degree days based on the projections into dates for that, excuse me, I hit the wrong button. Dates for that year. This was, say, this was 21. The thermal units are on this side. The first thing it will give you is historical average. What happened what were the temperatures from 1980 to 2010, indicating that maybe heat unit accumulation is now increasing. And then this is the projection for the heat unit accumulation and the actual heat unit accumulation during the same year. Okay? Then the next thing it gives you is what you can expect in terms of completion of these different stages. So here, basically, this is 90% of when the hull is fully formed, late May. The green line is shell firmness, which you can see about 90% of it is done by mid to late August, but it continues. And here in late July is 90% of the kernel growth, suggesting when the harvest date will be. As I said, this is not a calculator, it's a decision support tool. Use it to ground truth your situation. Okay. After we developed this model and put our information into that decision support to a website. Barbara Blanco Alate and her graduate student, Julia Adescavage, and Julia further developed the model by, one, defining stage 2 as a transitional stage, because as you can see, as the Spanish people said, the shell looks pretty fully grown here at 500, but it still continues to thicken and enlarge slightly up to 1,000. And Julia and Barbara added a new stage beyond the model we developed. They added the growing degree days for ripening as distinguished by hull color and hull condition, specifically the presence of tattering and the presence of the splits as Georgia described. Okay. So this was done, and this work is still being continued by Dr. Blanco Alate. Now we're going to talk about the final part of the season, key temperatures influencing entering dormancy, entering the fall. Just like spring, with unexpected temperature increases or temperature drops, and how we have learned how we're learning the effects on yield and nut quality the hard way. We also have learned our lessons about entering dormancy when they occur the hard way. This is Goose Lake Slough, Kern County, May 2009. We got called out to this orchard by Craig Kelson. And what I want you to notice is these trees are fully leafed out, look like they're moving on, to productivity. And these 6-year-old Golden Hills on UCB1 were dead. Basically, with the phenomenon, Craig did a very complete paper on it. It was called Winter Juvenile Tree Dieback. And the consensus was basically, it was a warm fall. This was a very saline situation, so the ground was still, the soil was still had a fairly high water content. It was a warm fall. There was a sudden freeze, and the temperatures damaged, in some cases, and killed the young, actively growing, non-bearing scions on a UCB1 rootstock. So basically, what we are learning is that with these more erratic temperatures, and this seems to be this phenomenon of young, actively growing, non-bearing trees, trees you invested 6 to 7 years in, are at danger of freezing if there are sudden temperature drops and the tree is still actively growing. If the tree has not been forced into dormancy with a zinc spray or an early to mid-August irrigation cutoff. The only other data we have on rootstock, young budded rootstocks was in 1990. We had 4 to 11 degree Fahrenheit temperatures up in Butte County. They killed 2-year-old PG1 rootstocks. The Integrarima and the Atlantica rootstocks in the same orchard did not die. Okay, so I'm just going to summarize this. First, I want to say that I want to reiterate, one, all growth and reproduction in a pistachio is a function of heat accumulation. Most of the data we have is exactly that, heat accumulation. We do not have much data about the variations of these temperatures during the season, either during winter, except for that one report from Australia, and the data that we have collected from sudden fall freezes or early spring high temperatures during bloom, okay? So dormancy, we have experimental data for chill units, but exactly how dormancy is affected by changing temperatures, as Julia said, dormancy is a black box. We don't know much about how it actually works, okay? Bloom and nut set, we're learning what spring temperatures can do to fruit yield and quality. The earlier work in this was done in another group in peaches by Ted DeYoung, and the results that we see thus far are consistent with his, in that early heat or unexpected coolness during bloom and fruit set, and also the information Elizabeth gave us today about pollination demonstrates that some of the unexplained things we saw in 2024 may be explained by the temperatures during bloom and fruit set. Nut growth and maturation, we're starting to get information about the difference among cultivars, but as Julia pointed out, photosynthesis is strongly affected at temperatures above 100 degrees Fahrenheit, and as Steve pointed out, that year we had a lot of, 2024 I believe it was, we had, I've forgotten how many days over 100 degrees. This is sure to affect photosynthesis. The effect may be delayed, but in terms of carbohydrate accumulation, but it could even have an effect not only on the current year's crop, but the following year's crop. And entering dormancy, our only information we have is from extreme weather events, which appear to be more frequent. Okay. Now what I'm going to do is synthesize the research from, or give you examples of ongoing research from colleagues that will perhaps give us some more information about temperatures during these phases. Okay. So first I'm going to talk about a chill assay done by Ivan Bermudez, a student of Patrick Brown's and mine. And what we decided to do was determine the heat required for bloom at different chill portion accumulations. In other words, if we had higher or lower chill, did we need less or more heat in the spring for successful bloom and development among the different cultivars? So the way this was done was what they call a bud forcing assay. We had 15 sites throughout California. We collected dormant twigs from commercial orchards at different chill portions. We focused on Kerman, Lost Hills, and Golden Hills, but I'm only going to report Golden Hills and Kerman. The twigs were placed in a greenhouse that simulated mid-April weather and evaluated for 60% floral bud push, which is what we considered successful bloom. And this is what we came up with and a predictive model that Ivan produced. The purpose, as I said, was to predict the growing degree days that was required for 60% bloom at different chill portions. We have Golden Hills and Randy here. We put the pairs together, and Kerman and Peters here. We have chill portions on this axis. On this axis, he chose to do growing degree hours because we were dealing with a shorter period. And what I'd like to show you here is that Dan Parfit and Craig Kelson did a good job in selecting Randy and Golden Hills because here they're tracking along nicely together. At equivalent chill portions, say 50 to 52 here, they both required approximately 5,000 growing degree hours for 60% successful bud push. Kerman and Peters, this is one of the reasons we've had the problem with them over the years. At the same chill portion, they have different heat requirements. Okay. So to summarize this, at 50 chill portions, the Golden Hills and Randy required about 5,500 growing degree hours. That's about 26 April days. We're about approximately 100 growing degree hours apart. That's about 1 day in April. So there's a good chance for synchrony there. The Kerman and Peters, they required more growing degree hours, approximately 33 April days, and were approximately 800 growing degree hours apart. That's about 4 April days. And as Elizabeth showed you in the sequence of pollination, 4 days can be the difference between non-fruit set and fruit set. At 60 chill portions, Golden Hills and Randy only required about 3,300 growing degree hours, 16 April days, and we're only, again, 100 growing degree days apart, less than 1 day in April. Good synchrony. Kermit and Peters required more growing degree days, 550, and we're approximately 400 growing degree days apart, which is why we sometimes see in poor chill situations, Kerman not meeting the needs of Randy. Peter's not meeting the needs of Kerman. Just wanted to show you here the difference in the 3 cultivars in their growing degree day requirements at the different chill portions. You can see that Golden Hills and Randy are, Golden Hills and Lost Hills are quite close together and require less heat units. So this is the first time we've had the estimation of the chill hours that Golden Hills and Randy needed. Craig showed they bloomed earlier, but he never did characterize the chill hours. But we can see here that they can bloom very well from 50 all the way up to 60, whereas Kerman requires more chill. Okay. One other thing we did was that we not only measured the ambient air temperatures, but we put little temperature sensors on the buds just to see if the buds were as cold or colder or warmer than the air temperatures. The logic in this is that, as Julia pointed out, and that Steve had that great shot of the fog in the valley, we've lost those fogs, and as a result, the sun is shining on the buds during the daytime. And when sun shines at a dark surface, all of you know that by your black steering wheels, the surface gets warmer. So the logic is perhaps the bud is not feeling the temperatures that not feeling the ambient air temperatures. So basically, in this graph, what we have is down here we have chill portions. This is just 2 buds we instrumented. Up here we have the bud chill portions. Here we have the air chill portions. If bud and chill portions were 1-to-1, if they were the same, this would be the line of, this would be the diagram. But here we can see at 40 chill portions in the air, the bud was at approximately 37. So this was this was only preliminary work for us, but we were able to demonstrate that perhaps the bud isn't feeling what the air is actually delivering. Julia has done a much better job of this in cherries, where she put out much better instrumentation than we had. Here it is in her cherry orchard, and did approximately the same thing, but got much more complete results than we did, in which she's now already developed into an app that you can see down here. But on this, she has the accumulated chill portions on this axis, and the measured tree temperatures here, the measured air temperatures here, and based on the app they developed, what she would predict as the actual chill accumulation on, I believe her sensors were on the bark. But basically, this model she developed will tell you that if your air temperature is this, and you have sunny temperatures, your tree temperature your tree temperature would be this, the blue line. So there's now a way to better measure the chill that the tree is actually seeing. Julie, is this app up already? She said yes. Okay. Sorry, went too fast. I just want to say, highlight the temperature-based work that Barbara Blanco-Alate and Julia are continuing, and they're starting to add other parameters like nutrition, nut quality, oil, the different oil components in the nut. But one of the, I think the best things they're doing is they're also showing the production of split nuts as a function of growing degree days, as you see down in this graph. So between 2000 and 2600, the percentage split will go from essentially 0 to almost 70% split. That paper out of Australia, also by a fellow called Jianlu Zhang, said the greatest predictor of split was heat accumulation in the summer. Okay. The other thing Barbara is starting to work on focuses on the color development in the ripening nuts. Now there's a lot more, there's beginning to be ground-based spectral yield and harvest timing estimating technologies. Translation, that means a little quad that can run through the orchard at 10, 20 miles per hour, has spectral lenses on it that can analyze color and or green nuts or perhaps ripening nuts and give you as a nut count the percentage of nuts you have and the ripeness stage they are at, or just the percentage of nuts you have on the tree if they're, the number of nuts you have on the tree as a function of spectral analysis. Translation, it can be used as a yield estimator or a harvest estimator. This is still experimental work, but the way technology is changing, it may be a possibility for the way to estimate. How am I doing? I can't see you with your sign. I'm almost done here. Okay, thank you. I couldn't see the sign. So anyhow, I'm saying technologies based on spectral analysis, based on nut color, may be developing for better estimating yield and ripeness timing. So there's another technology for telling you when you might need to harvest or how much crop you have. Okay, last thing Barbara is working on is possibly coordinating through growing degree days as the common metric, the now generations, not based on flights, and the whole susceptibility of pistachio to navel orangeworm. So there may be, through temperature, ways to coordinate pest management. And the last thing, and this is the thing that's keeping me still on my job, because I don't want to see the olive industry die on my watch, the table olive industry, and they're dying due to hand harvesting costs. Georgia is alluded to this, but we have been working with a seed. It is it's a new ethylene releasing compound that releases the ethylene, not its analog, in a more subtle and even way than ethyl or ethafon. And we have been using it in the combination of the newer spacings, the mechanical pruning, and the mechanical harvesting of olives to try and develop mechanical harvesting of olives. So Georgia will be continuing this work, hopefully in pistachios, to show that perhaps a seed can increase the harvest efficiency of pistachio, meaning you can get a higher percentage of the nuts off the tree. A seed doesn't advance harvest date. It only increases harvest efficiency by forming that fruit abscission zone. And the work that she's doing is modeled after what we have been doing at Georgia. Becky Wheeler-Dykes, the farm advisor in Glenn County, and I, in determining when to spray a seed as a function of growing degree days and decrease the pull force and increase the efficiency of harvest. So hopefully this kind of work will now be done in pistachios. Okay, so I said at the beginning, temperature is uncontrollable. So why are we even talking about it? Well, as Julia pointed out, the only thing we can do is try to grow the best trees we can with the best leaves we can and balance the carbohydrates. So we weren't going to greatly change a lot of management practices, but based on temperature, we may be able to change the timing of some things and the use of some things. For example, dormancy. We may, through the work that's going on, be able to determine if and when we should apply Dormex. If we don't have those chill portions by the end of February, if we're traditionally in an area with low spring temperatures, maybe you should be applying Dormex, and it is registered. Better determine irrigation timing for that transitional stage that Barbara better defined, that stage between the maximum shell size and the beginning of nut growth. Perhaps in that transitional stage, you can do deficit irrigation and predict it better. We might be able to better predict pest management growth for navel orangeworm by coordinating the growing degree day units for both the navel orangeworm and the pistachio hull susceptibility. We might be able to better predict harvest date for maximum quality if a seed is effective, maybe when to apply it, we can increase harvest efficiency and maybe decrease that second harvest. Maybe if we increase the harvest efficiency on the first harvest and do a strip harvest to determine what's left on the tree, maybe the quality and the yield aren't worth it, okay? And especially, we might be able to with better monitoring of temperatures, to explain the effects on yield and quality that we've seen in the past couple years that we really couldn't explain except maybe by temperature anomalies. So annual records, just keeping annual records will reveal changes in temperature over time, and we will learn the effects of extreme temperatures at different times. So with that, I thank you, and you all get to go to lunch. Thank you very much.
Thank you, Louise.